This is a lesson on logarithms, which is the inverse function of the exponential function. And the warm-up for this lesson would have been a warm-up of a function that we've done before. So we're going to slide. Definition of a logarithm. First of all, if we're going to do this all in terms of exponentials. If y is equal to b to the x, that's the way we've been using this, then the power x is equal to log base b of y. And so what we've done here is we have written this exponential as a power. X is the exponent. That means that's also an exponent. So what we're going to do is rewrite some of these in exponential form. So this log base 2. Base 2, here's the b, here's the power. Alright, b, power. So b to the x, like this. So we'll go 2 to the 5th equals this number that's left right here, the y, equals 32, and that is a true statement. So let's look at the next one. So we take our base, 1/5, we're going to raise it to the negative 2 power, and that is actually equal to 25 because 1/5 of the negative 2 is the same as 5 squared. Alright, so basically what a logarithm does, it says, what power do I have to raise 3 to get an 81? Now there's a couple of approaches to do this. If you know that 3 to the 4th is 81, you can just write equals 4. Or you can say that this is equal to x and rewrite it exponentially and go 3 to the x equals 81, and 81 is 3 to the 4th. And here's a fact. If the bases are the same, the exponents are the same. So essentially what you're doing here is canceling the base, and what you're left with is x to the 4th, x equals 4. Same type of thing with log 64. What power do you have to raise 64 to get a 2? Now this is a situation where it actually is much easier to set it equal to x. And we say 64 to the x power is equal to 2. Now can I rewrite 64 with a base of 2? And I can. 2 to the 6th to the x equals 2. And I'm going to write 2 to the first power. And that gives me 2 to the 6x equals 2 to the first. I'm going to cancel the bases, solve for x, and that gives me x equals 1/6. Now for this slide, common logarithm gives you a base of 10. Because it's common, which means this is the number system that we use, this is the button that's on your calculator, we are assuming that the base that would normally be written here is 10. So anytime you see a logarithm without a base written, it's going to be a 10. Now the second thing, the number e that we talked about, that irrational number, also being a exponential, has an inverse, and we could write it like this, but to distinguish it from the common logarithm, we write it and we read it natural log of e, even though it's an L in the front. Alright, so given that exponentials and logs are inverse, let's have some fun. So if I have log base b, and then I have a b to the x, what happens is the log b and the number b cancel, and what you're left with is equal to x. Now another thing that we can have similarly to that, except with the natural log, is that we would have natural log of e to the x. Now remember, it's understood that there is a base e right here, so e and e, like b and b, and that's going to give me equal to x. But what if I switched it, and then I have b, and I have it raised to log b of x? What we're essentially doing here is composing an exponential and a logarithmic function, and it does the same thing, just like that. And then if I have e raised to the natural log of x, that's also equal to x. And so these are some basic inverse rules that you're going to need to memorize. So e natural log of 9 follows this rule right here. X is in the place of the 9, so this is just equal to 9. This one follows this rule right here. And negative 3x is in the place of the x, and this is just equal to negative 3x. Now to find the inverse function, remember that when we find inverse, what we're going to do is switch the x and the y. And since the inverse of an exponential is a log, you can expect that this is a logarithm. So what we're going to do is rewrite this exponentially, and we're going to write it logarithmically. It's already exponential. So what we're going to do, we're going to have a log, and we have, where's our base? The base is 8. I'm going to put that in. And the number that it equals is this x right here. So we're going to put that in, and that is equal to y, which is now the power. So remember, logs are power. Now the same type of thing, inverse of y is equal to natural log of x minus 4, we're going to use a base of e on that problem. And I'm going to switch the x and the y. So x equals natural log of y minus 4. I need to get the y out of the natural log. You cannot distribute the natural log through that parentheses. But what we can do is write this exponentially. So remember, this is a base of e that is implied to be right here. And remember, logarithms are power. So you can go e to the x. E to the x equals y minus 4. And then it's just a matter of adding the 4 to get your function. Last but not least, for the new notes, parent graphs for logarithms. Now, we discussed that the graph of an inverse reflects over this diagonal and this diagonal. So we're going to be thinking about this inversely. We also know that the domains are opposite. So I'm going to take this, domain and range are opposite. So that means 0, 1's on this exponential graph. So what that means is that 1, 0 right there is on the logarithm. And so we can find some other convenient points and switch those as well. Like this is 1, 3 right there, so I want to go to 3, 1. So that's another option right there. And what I see is that right here, my domain is going to be over 0, but that means my range for my inverse needs to be greater than 0 also. So a good rough sketch of this logarithm goes like that. And that would be the inverse of a growth function. So same thing on the other side with a decay function. We have our 0, 1 right here. So I'm going to flip those points over, make a 1, 0. And then I also see that I have, that's a 2, looks like a 2, 6 right there. So I'm going to go to 6, 2. And it's about right there. And this one actually does kind of flip over the other one. Oh, I have the wrong signs on that. Let me erase that. Let me fix that. All right, that's negative 6, 2. So we'll have 6, negative 2. I knew I was going the wrong direction. So about right there. Okay. So it's going to kind of flip over, kind of like that. The idea is that that diagonal serves as a reflection. But we don't have to do this. We don't have to graph an exponential and then flip it. So let's see, graph this. All right, so the easiest way, I'm going to start with graphing just log base 3. of x as a parent graph instead of doing the -2 and the +4 for right now. Since the logarithm is an exponent, it makes a lot of sense that right here in the x's, we're only going to use powers of 3. So I'm going to start with 1 and 3 and 9. What we're asking ourselves is 3 to the what power equals 1. 3 to the x equals 1, and that's 0. And then how about 3 to 3 with a 3? That's a 1, and then that's a 2. So our domain here is all real numbers, and our range, actually our domain is not all real numbers. Let's switch that. Our domain is, let's see, yeah, it is real numbers. We can put negatives in. Or actually, no, we can't get negatives out. But we're going to go 1, 0, 3, 1, and then 9, 2 is way on over here. We're going to do this. Okay, so your domain, x, has to be greater than 0. Now your range, sometimes I have to look at the graph first. Now your range is actually all real numbers. Remember, they swapped. Your domain and range swapped. Now, the x and y for the new function, this is the one I actually want to graph. Remember, the -2 means we're going to go 2 right, and the +4 means we're going to go 4 up. Okay? So we're going to start with that 1 right here. Okay? And we are going to add 2 to it, so that's 3. Now if you look at plugging it into the equation, you get 3 minus 2 is 1, and that gives you a 0, and then you add 4 to it. So we've got 4 right here. So you're going to add 2 to your x's and add 4 to your y's all across the board. So you've got 5, 5, and then you've got 11, 6. Now that last one is not going to fit on this graph, but we're going to make the best of it. So we've got 3, 4, 5, 5, and then 11, 6 is way on over there. Now this -2 right here means that we have shifted our asymptote from the y-axis to right here at x equals 2. So we're not going to cross that line. So I'm going to connect this and connect that, just like that.